we will now move to the topic of shared memory using clocks. So here is a review of shared memory. We have studied this in the first part of the course, but this is a review just to remind you. So we have a set of registers. We can perform two operations on each register. A write operation to update the register value to V, and a read operation that returns the register's value. And what we are interested in this unit and the next units is to talk about linearizable shared memory. So let us remember the correctness condition of linearizability. So linearizability requires the following condition. If an operation O1 returns before the invocation of operation O2, so here is the response or the return of operation O1, and here is the invocation of operation O2, then O1 must be ordered before O2 in the history or the execution. So the linearization point of O1 is before the linearization point of O2, which would mean this linearization decides what are the effect of each operation in that sequence. And this has to be consistent. The algorithm that we studied before in the previous part 1 of the course is the read, impose, write, consult majority algorithm. And what does this algorithm do? It does 2 round trips to a majority of processes for both reads and writes. So here is a typical example. We will show you how the read operation is performed and how the write operation also is performed. Both operation has 2 phases. One is called the query phase and the second one is called the update phase. A read operation consults now a majority of processes, and this consultation, it is this query phase. When it gets a majority, in this case here, 2 out of 3, so it has read a value and a timestamp. Now it takes the value with the highest timestamp and perform an update operation. And when it gets a majority, then the read operation is complete. That was the read operation in the read, impose, write, consult majority. The write operation also has 2 phases, the query phase. The query phase is inquiring about the highest timestamp, and once it gets a majority, then it uses this timestamp to increase its timestamp and perform the write with a new timestamp higher than what is existing. You will see this in detail. We have 2 phases for the read and 2 phases for the write. So we have seen this in the section on shared memory and the algorithm that provides linearizable read-write registers. So let us look in detail to remind each other about what are the different phases. So a phase first is a round trip of communication to a majority of replicas. And as we've seen from the previous picture, the first phase is called the query phase, and the second phase is called the update phase. A read operation, so a process PI invokes a read operation. So in the query phase, each process responds with the highest timestamp value pair. So now the process has received a majority of timestamp value pairs. And in this case, PI picks the highest timestamp value pair received in the query phase. And we denote this by TS and B. So a highest timestamp value pair means that the timestamp here is the highest. So this is the most recent write. So that is, and he should read the most recent write. Then before he returns the value V, he performs the update phase using this pair. And why is that? The reason for this is the following, and you can see it here, is that if we do this, any operation invoked after this read operation is completed is guaranteed to see a timestamp greater or equal to this TS. So an operation that happens after this read operation cannot read, for example, an old value. We can optimize the read operation by basically avoiding doing the update phase, the second phase. If all the timestamp value pairs that we collected, are collected from a majority, are the same, then the update phase can skip. Because in this case, there is always a majority for this timestamp. So any other process that performs an operation will always see this timestamp value pair. So this works since a majority of the processes already store timestamp value pair with a timestamp greater or equal than TS. So in this case, there is no possibility to read an old timestamp. That's why in the first place we needed the update phase. But as long as the processes in the majority respond with the same timestamp, so we are guaranteed that any other operation that comes after that will observe this timestamp or a higher value. Of course, in good conditions, the network is stable, low contention, this is likely to be the case. And the read can complete in most cases in one round trip, which basically says that in most cases, a previous write operation has completed. If we look to the write operation, on the other hand, so the process invokes the write operation, and the query phase is to get a knowledge what is the highest timestamp value pair in the system. So in the query phase, each process responds with the highest timestamp value pair received, and after the query phase, PI picks a unique timestamp higher than all timestamp received and pairs it with the value to write. And then in the update phase, each process stores this timestamp value pair if this pair is greater than the timestamp that is previously stored at that register. So we only update the timestamp value pair if the newer timestamp is higher. So the write operation takes two round trip, a query and an update. So the next step is to see if we can optimize the write operation. And here comes the issue of clocks. Remember that the reason for the query phase is to create a timestamp higher than all previous timestamps. So if a process have access to clocks, it is possible to skip the query phase. Process PI invoking a write, it instead picks the timestamp by reading its own clock. So this is the current time of its own clock. This is at this moment the value of the local clock, and this is the process ID. The timestamp are timestamp PID pairs now. So the question how well clocks are synchronized will determine if we can implement linearizable atomic registers or not. As it's written here, how well the clocks are synchronized determines if the atomicity property of linearizable registers is satisfied or not.